Yes, ma'am, your screen is visible.
Okay. Hold on. I think the network here is very slow today. That's why some problem. Okay, so it is visible now, right?
Yes, ma'am.
Okay. So, hi everyone, I am Riturani Mandal. Now you all will be aware about this. So, last two classes there was some problem with updating the portal. That's why it was not showing my classes are there. So, that's why the attendance was very low. So in last two classes we solved 2020. We have finished the 2020 inorganic chemistry part, and now we are solving 2019 chemistry solutions, inorganic chemistry solutions. So if you people have any doubt from the previous years also, you can ask me. Okay. Today we will be starting with this question, uh, which came in GATE 2019. Question number 17. So this is basically the question is the number of CO stretching bands in IR spectrum of trigonal bipyramidal cis MCO whole 3 L2 is how, like, here they are asking there are how many total IR active carbonyl stretching bands in this particular complex. Okay, so if you see this question like this, you will feel that this is an inorganic chemistry question, but this needs the concept of group theory for solving it. Okay, so here they have asked number of carbonyl stretching bands in IR spectrum for this compound, this MCO3L2. They have already given the geometry in this question, which is trigonal bipyramidal. That means the complex is like M. Okay. This is trigonal bipyramidal. Now they are saying cis. That means we will keep these two L, these two ligands, cis to each other, and then CO, CO, CO. Okay. So this is the structure of this complex. Now they have also said here that L is a monodentate ligand and M here is metal. So this is the given compound. Now the local symmetry around the central atom, like uh, here the local symmetry around the central atom is this trigonal bipyramidal that we saw C already, CO, CO, CO. So this local symmetry around the central atom of metal carbonyls decides the number and intensity of the carbonyl stretching bands in their IR spectra. And the number of IR active bands for a specific isomer can be arrived at by using group theory. So basically finding out the number of carbonyl like IR active CO bands. This is one of the applications of group theory. So now, you people are aware with group theory, and right? Hello, am I audible? Hello.
Yes,
Hi,
ma'am.
everyone is following, right? I just checked whether I lost the connection again. Okay. So, for solving such kind of questions, first we should know what is the point group of this given compound. So, anyone, what is the point group of this compound? So, this is this Ml2CO3. Uh, Now we will, like, if can anyone tell me what is the point group of this? A try. Okay, first look for it. Does it have any CN axis? CN means the principal axis. Is it having any principal axis? Anyone? Okay. So, actually, if we see, there is no principal axis in this complex. Only there is one sigma plane, which is this. Like, okay, I will take another color. If we take this plane, this means that the plane will be from this, it will cut this L and CO, okay, and it will bisect these two carbonyls. You understood which plane I am talking about. So this compound basically just have only one sigma plane, and we know that every compound is having this identity element E, and except for that there is only one sigma. So compounds which just have E and sigma H, the point group for them is CS. Okay, so this compound belongs to CS point group. Now moving on to the reducible representation for cis MCO3L2. Okay, so first we have to write the reducible representation for this. Now we know that the only operators are the only two operations which are there in this complex are E and sigma H, right? Now for writing reducible representation of this thing, how we can write this is this reducible representation we denote as like this. So this is equal to character of E and character of this sigma H. Okay. So how we can know the like we can understand what is the character of a given operation? One simple way of knowing that is here there are three COs, right? Let us make three arrows for these three COs, okay? And number them as 1, 2, and 3. So characters are number of unshifted arrows for that operation, okay? So now if we do identity operation in this complex, then what will happen? There are three arrows. We will check that how many of them are remaining unchanged, which are unshifted. How many of them are remaining unshifted after the doing operation E on this compound. Okay. So since this is identity operation, none of the three arrows will be shifted, and therefore the character of E will be 3. Okay. Then for sigma H, what we say, this is the plane. This is the only plane which is present in this compound, and this plane is cutting this CO. Okay, this third CO. That means this is remaining unshifted, but because of the presence of this sigma plane here, this 1 and 2 will get interchanged. That means they are getting shifted. So when we are doing the operation sigma on this compound, only one of the arrow is remaining unshifted and the other two are changing. Okay, so it is the reducible representation we can write as 3e plus 1 sigma. Okay, this is the thing. Now next, what we have to do is reducible representation is further broken down into its irreducible components with the aid of character table and reduction formula. So this is the character table for CS point group. There are only two operations E and sigma H, and this will give rise to these two these, these two, A dash and A double dash, and this will be the character. A dash will have 1 1, A double dash will have 1 and minus 1, and like you will and these are the linear rotations for this and quadratic notation. And so this is the character table for CS point group. So CS point group is a very simple point group, so we can remember this. Okay, and there is this is the reduction formula by which we can reduce this break down this reducible representation into its irreducible components. So the formula is, say, uh, n species. By species here we are meaning a dash and a double dash. This is equal to 1 by g summation of or summation over I gi this chi reduced into chi table. Okay, where n species means number of times the species contributes to the total reducible representation. Here species will be A dash and A double dash. This we are calling species. What is G in this equation? G is the order of this point group, which is equal to the total number of symmetry operation in this group. So 1 E and 1 sigma H. So the G of this point group is what? Anyone? What is the G value? What is the order of this point group? It's 2. Okay. Then next is GI. What is GI? Number of operations in the symmetry operation class I. So this we are calling one class. Okay. This is one class and this is another class. So for few point groups, we can see like for D4H kind of point groups, we will see that there might be two like some prefix in front of these operations as well. So this GI denotes that, but in this case, for both this class and this class, for both of the classes, the GI is 1 only. Okay. Then chi reducible is total character of each operation found in the reducible representation, and chi table means character of each symmetry operation in each species. These are individual characters. So this is chi table, and chi reducible means this which we found out. Chi red means 3 E and 1 sigma H. Okay. So using these two, like using this character table, this reducible representation and this reduction formula, now we will find out n species, that is the number of each number of times each species contribute to the total reducible representation. Let's find out for first n a dash. Okay, so n a dash 1 by g is 2, that is the order of this point group. Then GI, I said for both of them it is 1 because this is 1E and 1 sigma H. So it is 1 into chi reducible, that is 3 into chi table, that is 1. Okay, this one plus again uh, this I 1 by G I have taken common, and then for this operation what will be it? again 1 into 1 for this chi width is 1 and this character is again 1, right? That means it is 3 plus 1 by 2 or 4 by 2 which is equal to 2. That means this A dash occurs twice in this reducible representation. Okay. Then for an A double dash, it will be again 1 by 2. Now we will see for this one. So what is this? Again, this is 1. So 1 into this value is 3. 3 into this value is 1 plus this GI is 1. Then what is this? Chi reducible. This is 1 and sigma h, that chi from table, this is minus 1. Okay. That means here it is 3 minus 1 by 2, right? Which is equal to 1. That means the reducible representation, now we can write it as 1, 2 A dash plus 1 time A double dash. Okay. Now the thing is that for only those are IR active where like it is transforming into, here like we can see that A dash is transforming into Cartesian coordinates x and y. Also A double dash is transforming into Cartesian coordinates z is present. So if anything among x, y or z is present in this linear rotation column, then only that species, or that particular uh, what to say, like here both A dash and A double dash will be IR active, okay, because both of these two are transforming into Cartesian coordinate x, y or z. So two, here we can see the 2 from this A dash and 1 from this A double dash. So we are getting a total of 3 carbonyl stretching frequencies, okay, that is 3 active IR bands. Now you all will be thinking that all these things, do we have to go through, like do all these things in exam, because it will take a lot of time, right? So there is like, this is kind of trick you can say. So highly like compounds which are highly symmetric, okay, highly symmetric metal carbonyls gives lower number of IR active CO stretching bands. So what are highly symmetric metal carbonyls? We will say octahedral complexes. By octahedral, I am meaning that if all the coordinated ligands are same. Okay, so this is an highly symmetric complex. If it is octahedral or tetrahedral, where again all the ligands are same, or DNS type of groups. Okay, so they are having lower number of IR active CO stretching bonds. They have IR active number of IR active CO bond bands is 1, mostly for these cases. Okay, then metal carbonyls with lower symmetry gives higher number of IR active carbonyl stretching bands. So metal carbonyls with lower symmetry, in that these point groups will fall like CS point group, the one which we discussed just now. Okay, so for this case, number of IR active CO bands is equal to number of CO in the molecule. So in this molecule, how many COs were there? 2, right? Sorry, 3, right? So that's why we saw that at the end we got total 3 number of IR active stretching bands, right? Then C2B molecules with C2B point group, for them number of IR active bands is equal to number of CO in the molecule. Okay, the example you can take Like let's say MCO4L2. Okay. So in this case also we can see in this case also this thing is having C2B point group and uh, 4CO are present there. Okay, so number of IR active CO bonds in this molecule is 4. Okay. Then for CNB type of molecules where N is greater than equal to 3, the number of IR active carbonyl bands is equal to number of carbonyls in the molecule minus 1. An example of this is MCO3L3. Okay, the phase isomer of this. Okay. So here the point group of this molecule is C3V and it is having here 3 carbonyls present, then 3 minus 1, 2 IR active bands are there. So this is these are the tricks like this these things you can remember so that you will be very easily you can solve a question. Okay. So I hope it was clear to you. So here the answer for the number of CO stretching bands in IR spectrum of trigonal bipyramidals is MCO3L2 is 3. Okay, so 3 will be the answer. For knowing more about this group theory and its chemical applications, you can go through Professor Manavendra Chandra's NPTEL lecture course. He is from Department of Chemistry, IIT Kanpur. This is the link given for this lecture series. You people can go and go through this for getting more insight into this. Now, any question from this? Anyone? Hi. So, is it clear to everyone?
Yes, ma'am.
Riyasat and Gunasli, it's clear?
Yes, ma'am.
Okay. So you can remember that trick. It will help in most of the cases. Mostly if you have any complex like octahedral, tetrahedral, they will definitely have with like if all the ligands are same, they will have only one IR active CO carbonyl stretching frequency. And for the CS C2B, these also you will always get like the whatever that formula that trick says. So it's easy to remember, but from where it is coming, that was the whole thing. First, you have to know, like, go find out the point group. Then you have to write the reducible representation of that. Then break it down to its irreducible representation, and then see among them which are the species which are like transforming into the Cartesian coordinates, and only those will be the IR active ones. Okay. So we can move on to the next question. So the next question is this. This question is also from GATE 2019 chemistry. Uh, okay, question number 29. In In the EPR spectrum of a methyl radical, the number of lines and their relative intensities respectively are option number A 1 and 1, option number B 3 and 1 is to 2 is to 1, option number C 4 and 1 is to 2 is to 2 is to 1, option number D 4 and 1 is to 3 is to 3 is to 1. Okay. So they here in this question they are asking that for methyl radical, what are the total number of lines we are getting and the intensity, relative intensity of those lines. Okay. So for any molecule to be EPR active. First of all, what is EPR? EPR means electron paramagnetic resonance. So the conditions for being electron like EPR active is that there should be at least one unpaired electron present in that molecule, and the I value should not be equal to 0. The spin value should not be equal to 0. Okay, so these are the conditions for being EPR active. Now, so what are mostly EPR active complexes are like all the radicals, they are EPR active. Then, say, if transition metals which are having unpaired number of electrons, as we see, like let's say we are having an octahedral complex which have, let's say, D2 system or something. So here we can see there are two unpaired electrons. So this complex will also be EPR active. So, okay, now in this question, what they are saying is for methyl radical. Now, since it is methyl radical, it is EPR active and it is having 3H and 1 radical. Okay. So, for finding out the number of lines in the spectra, we will use the formula the same as we use for like uh, NMR, is 2Ni plus 1. Okay. So here 2. So what is N? N is these number of hydrogens. Okay. So this radical is directly, this is on C and it is directly connected with 3 hydrogens. So here the N value will be 3 for presence of 3H. And what is the I? The IH is half. Okay. So it will be half plus 1. 2 will get cancelled out. So it will have 3 plus 1. Okay. 4. 2. So this will have 4 lines. So first only we can see that then this and this is not the option, right? These are not the correct options. Then next, moving on to their relative intensities. Now, how do we find out relative intensity? So here also H is having half spin, and we know, like similar to that of NMR, we know that if the spin value is half, then we can use Pascal's triangle for getting the relative intensity of those compounds. So what is Pascal's triangle? This is 1, 1, 1, then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So how this happens is, let's say this is 1. So there is nothing. That means if we consider this 0, then these addition of these two will give this. Addition of these two will give this. Okay, now again this 1, addition of 1 plus 1 is 2, and here this will come as 1. Again this will be 1. 1 plus 2 is 3. 2 plus 1 again 3. Then here 1 plus, here nothing is there, so 1. Like that Pascal triangle goes on. Okay, then here again 1, then 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and here 1. So like this we can write it, like it will go on and on and on. Okay, so this is the Pascal's triangle. We already found out from this formula 2Ni plus 1 that here the number of lines will be 4 lines. So now you tell me what will be the intensity then? Anyone?
1:3:3:3.
Yeah. So for 4, this will be the intensity, relative intensity, that is 1:3:3:1. So the correct option in this question, in the EPR spectrum of methyl radical, the number of lines is 4 and their relative intensities is 1 is to 3 is to 3 is to 1. So among the options, all the four options, this is the correct answer, option number D. Okay, is it clear?
Yes, ma'am.
And this is like principles and applications of EPR spectroscopy by Professor Ranjan Das from Department of Chemical Sciences, CIFR Bombay. So he have made a series of lectures on this EPR ESR spectroscopy. You can go through it for more knowledge about this topic. Um, it was clear to everyone, right? We can move on to the next question.
Yes, ma'am.
So next is question number 32. So this is question number 32 from GATE 2019 paper. Uh, the question asks for match the metalloproteins with their respective functions. So this is again a chemistry, a question from bio inorganic chemistry. Okay. The metalloproteins about which they have asked are ferritin, rubredoxin, cobalamin, and carbonic anhydrase. And in this side, they have given the functions of these. Okay. So, first of all, then we will discuss about ferritin. So, ferritin is, anyone knows what is ferritin? I have already written here. So, ferritin is the main iron storage protein in human body, also in other animals and all. But we know that in human system also, ferritin is the largest Fe storage protein. And there are 24 subunits of this protein. It is kind of a spherical hollow type of shape it has. Okay. Okay, so it has some tetrahedral kind of void inside. These 24 subunits they will make like all this, and inside there is one hole. Here they store this iron. Okay. So basically, like it is, you people should know that it enters the body. It enters ferritin as Fe2 plus, but then there it gets oxidized and it is stored as Fe3 plus inside ferritin. Ferritin can store about 4,500 Fe3 plus ions. Okay. So, what is the function of ferritin then? Among the given options, electron transfer, acid-base catalysis, metal storage, and methyl transfer. So, that means ferritin is metal storage protein, right? Okay. So, the next is rubridoxin. What is rubridoxin? So, there are various iron sulfur proteins, and rubridoxin is the simplest iron sulfur protein among them. So all these iron sulfur proteins, these are electron transfer proteins. Okay. So why, and this here iron is bound to sulfur atoms. That's why we call them as iron sulfur proteins. Like irons are only bounded to sulfur atoms only. And this is, as I said, this is the simplest FeS protein, which we write often as Fe1S0. Why Fe1S0? Because uh, the, we also have another iron sulfur protein, which is ferredoxin. Okay. And ferredoxin consists of two type of sulfur. One is this sulfur from cysteine group. Okay, cysteine sulfur, and another is inorganic sulfur. So they are present as bridging moiety between these two. Let's say if we have this, and there will be S, sorry, not S, Fe, then S, and here these two are S from cysteine, S cysteine, 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 cysteine. So here we call this as Fe2H2. But in case of rubredoxin, no inorganic sulfur is present and only one single iron center is there, which is coordinated to four sulfur atoms from four cysteine moieties. It has a distorted tetrahedral structure. Okay, and also this ferredoxin, this is Fe2S2. Other two types, Fe3S3 and Fe4S4 are also there. And as we said, these type of proteins, these type of iron sulfur proteins are electron transfer proteins. So the role of this among the given options is of electron transfer. Okay, electron transfer. Now moving on to the next metalloprotein which they gave, it is cobalamin. Okay, it is cobalamin. So cobalamin is also a heme protein. So, what is a heme protein? Heme protein means that iron center and porphyrin ring will be there. Sorry, iron center and iron ring is what we say. But in this case, this is not porphyrin ring. It is a corin ring. But the difference between porphyrin ring and corin ring is just this CH. Okay, this one CH, it is which is present in that porphyrin ring. But cobalamin, it has corin ring where the CH is not present. Okay. So, this is the only vitamin which consists of this metal. It is having cobalt in its center. We can see that it is coordinated to four nitrogen from this corin ring, uh, and we can have different type of uh, cobalamins. It will be if this R is a methyl group, then it will be methylcobalamin. This R group can also be OH or CN, and these are known, like this cobalamin can transfer the methyl group to homocysteine to generate methionine and regenerate the enzyme bound cobalamin CO1 cofactor back. So one type of reaction which this cobalamin shows is methyl transfer, right? Methyl transfer. Since by transferring methyl group from homocysteine, they can make methionine. So the function of this among the given options will be of methyl transfer, right? Function is methyl transfer. And the last metalloprotein which they gave is carbonic anhydrase. So, okay, sorry, this thing is wrong. Thing which I saved, I was not showing you that one. Wait. Okay, sorry, that slide is missing. I don't know why. So, carbonic anhydrase is basically What carbonic anhydrase does is hydration of carbon dioxide. Okay, carbon dioxide. Hydration of carbon dioxide, CO2 plus H2O, and this is reversible hydration of carbon dioxide. From there, here we can find get HCO3 minus, which is bicarbonate ion. Okay. This plus H plus. So here we can see that from CO2 plus H2O, it can give HCO3 minus plus H plus, and again from HCO3 minus plus H plus, it can give back this. So this is an acid-base type of reaction, right? So among the given options, the function of this is acid-base catalysis. And carbonic anhydrase, little bit about its structure. So in this, the metal present is zinc in +2 oxidation state, and it is coordinated to 3 histidine moieties, and here OH or water is present. Okay, so from this we can now match. Ferritin means ferritin is an metal storage protein. Rubridoxin is what? Rubridoxin is an electron transfer protein. Cobalamin is doing methyl transfer, and carbonic anhydrase for acid base catalysis. Okay. So here P is option number 3. These two options are P option number 3. Then Q is 1. Okay. Th- that means this option is correct, where P is 3, Q is 1, R cobalamin is 4, that is methyl transfer, and carbonic anhydrase is 2, acid base catalysis. Okay. So in this question, question number 32, match the metalloproteins with their respective functions. Option number B is the correct option. And so you have any doubt? So for this, Francis NPTEL course from Debashish Rai. He is from IIT KGP. Okay, any doubts?
Ma'am, I have one doubt
Yeah.
that in cobalamin, that corin ring and porphyrin ring both are present.
No, 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 no. Only Korean is present. So it is just different from. I just
No,
said the difference between porphyrin ring and Korean ring.
no. Ma'am, you said that the hemiprotein includes Fe plus porphyrin ring.
This is what
Uh,
we say. That's the definition for like when we find out among hemoglobin, myoglobin, hemocyanin, and all those, that what is the heme protein and all, we say that a presence of Fe and porphyrin ring is necessary, but this is also a heme protein only. But in this case, it is corin ring. So there are few rings, this porphyrin ring, corin ring, and chlorine ring also, which is present in, I think, chlorophyll. So that is also considered as like that also satisfies the condition for heme protein. We call these also as heme protein. That's why I say, like, people might think that this is not a heme protein, but this is also a heme protein only. Okay.
thank you.
Uh, okay. Any other question? Clear then, everyone?
Yes, ma'am.
Okay. So we'll move on to the next question. Okay. So the next question is question number 26 from 2019. The question is the experimentally observed magnetic moment values with which match well with the spin only values for the pair of aqueous ions is. So the given options are option number A, chromium plus 3 and gadolinium plus 3. Option number B, cobalt plus 2 and gadolinium plus 3. Option number C, chromium plus 3 and dysprosium plus 3. Option number D, lutetium plus 3 and terbium plus 3. So here in the options we can see that transition metals are given as option and lanthanides are given. Right? So we know that magnetic moment arises from like two factors. One is the spin contribution and the other one is the orbital contribution. Okay, so for the movement of the electron on its spin, we get the spin contribution. On its own axis, we get this spin contribution, and orbital contribution we get for its like making like orbiting around a particular orbit. Okay, so we have two type of contribution. One is spin and the other one is orbital. Now, for transition metals, we know that uh, in this question, what they are asking is when the spin only values are equal to their observed magnetic moment values. So, mu observed is equal to mu spin only if no orbital contribution is there. Contribution is there. So, what are the given transition metal complexes in this case? Chromium 3 and cobalt 2, right? Okay, before that, we will just see this is the condition for having spin only magnetic moment as the observed magnetic moment value only for transition metals, and for lanthanides also is the same. So, only if we have electron configuration F0 or F7, that is half filled, or F14, that is full filled, then only we have mu spin only equal to mu observed. Okay. So now these are the complexes. These are the uh, elements which are given. First, chromium. So chromium is having how many electrons? D5s1, right? 3d5, 4s1. So chromium in plus 3 will mean 3d3, and here they have, so 3d3 means 1, 2, 3. Okay. D3 system. So my right cobalt. Okay. Then moving on to cobalt. Cobalt means cobalt and plus 2. Cobalt is having 3d7 and 4 is 2. Right?
मैम वो आर्गन होगा शायद, जेनन नहीं होगा.
Sorry. Yeah, I don't know. Xenon lanthanides के लिए है. तो मैं ये लिखती हूँ. Okay, so CO2 means this is 3d7. Then gadolinium is having C, it is xenon 4F 7 5D1 6S 2. Okay, so gadolinium in plus 3 state means it is 4F 7. Then terbium is, so here like they have also given the atomic number for all these complexes as well. So if you remember the periodic table, the yeah. This is terbium. Okay, so terbium is having 4F9 and 6S2. So this is its atomic number is 64. This is 65. Huh? So it is having this terbium 3 means it is 4F, 2 from here it will go and 1 from here. So 4F8. Then comes dysprosium with atomic number 66. It is having xenon 4F10 and 6S2. So dysprosium 3 plus means 4F9 6S0. Then comes lutetium. Lutetium with 71. The electron configuration for this is 4F14 5D1 and 6S2 plus 3 means let's see 4F14, right? Now this is the question. So yeah, here this will as we told said that for lanthanide only F0, F7 and F14 will have mu spin only value equal to mu observed value. That means this gadolinium and lutetium. These two are these two will show the mu observed is equal to mu spin only. Okay. So gadolinium 3 and lutetium. Okay. So these are present in these three options. The next thing is terbium, cobalt or chromium. Terbium is 4F8, so it won't be the case. So this is cancelled. And then cobalt 2 means D7. This also won't be the answer. Cobalt 2 plus means D7 complex. And where it is? Then chromium 3, which is a D3 system. Okay. So here, like GG. So this is filled, and that's why chromium 3 and gadolinium 3, this will be the correct option for this question. Okay. Why chromium 3? Because here we are having D3, right? So there will be no orbital contribution we consider if there was, like in this case, see, D7, right? 1, 2, 3, 4, 5, 6, 7. So if this type of complex is there, then it will have orbital contribution. But if we have D3 or D5 system or D10 system, they will not have any, or D8 system, they will not have this contribution, orbital contribution. But actually, I have one question. I know that D5 and D10 will not have orbital contribution, but I am not sure about this D8 and D3 both. So, sorry for this. I have a confusion. I will read more about it and I will tell you that why it is not having this orbital contribution. I am sure that gadolinium and this lutetium they are not having. but cobalt 2 also this can't have. But for this chromium 3, I will read this properly and I will get back. Okay.
मैम जिसका T2G set of orbital having unsymmetrical electrons that show orbital contribution size.
जिसका T2G set of orbital has
Unsymmetrical field of electrons. That means two electrons that contains if two T2G
like I mean
three.
you are saying that if it is completely filled, like then
No, no, no,
T3
no,
is
no.
also not
Unsymmetrical.
having.
Not completely. That is unsymmetrical. That means either two, either one, either four, either five.
Yeah,
Three,
like all are filled here. Oh,
three or
one is there in each.
6 are symmetrical in T2G, but D1, D2, uh, D4, D5 that are unsymmetrical.
Okay, okay.
हम कहीं पे पढ़ा था वो ठीक है कि गलत है क्या थोड़ा कंफ्यूज है.
So I will read it properly and I will get back. I don't want to say anything wrong. So I think this will is the correct answer, but because cobalt can't be the option and other options are wrong, but I will still read this properly. I am a bit confused about this and I will get back. Okay. So it is actually already time, but we will take up this quick question, question number 30. The product obtained in the reaction. Okay, anybody else having any other doubt in this question? Okay, I'm moving on to the next question, which is question number 13 from this paper. So the question is the product obtained in the reaction of Mn2CO10 with Br2 is the given options are option number A MnCO whole 5 Br, option number B Mn2CO whole 8 Br2, option number C MnCO4 Br2, option number D Mn2CO9 Br. Okay, so this question is actually a very simple question from organometallics. Here, what concept we have to use? This 18 electron complex. Okay, 18 electron rule. So we know that 18 complexes which are having 18 electrons, they are stable. Okay, so in this question, what we have been asked is the reaction is between Mn2CO10 and Br2. Fine. And what will be the product? So here we can see Mn means it is G7, right? So 7 to 14. Okay, we will Mn2CO10 is something like this. 5 CO each. 1, 2, 3, 4, 5. Okay. So Mn means 7 electrons from this. Because of this bonding between two manganese, 1, and then all CO will give 2 electrons each. So 2 5 is 10. Right. So it is an 18 electron system. So it will give an 18 electron complex only as the product. Now if we see, if we check the given options, option number A is MnCO whole 5 Br. So what is the total electron count in this? Valence electron count. Manganese is giving 7 electrons. 5 into 2, CO gives 2 electrons. So it will be 10 plus Br1. So this is satisfying 18 electrons. Now next moving on to this one. It is what? Manganese. Uh, this, right? Mn. Then 4 CO are there and 1 Br each. That means manganese for each it will be 7 plus 4 CO means uh, 4 CO means 4 to the 8, right? Then 1 Br and 1 bond. Then 8 is the section plus 1. It is all both like these two manganese centers are having 17 electrons each. Then it is not an 18 electron, not 18 electron. Then MnCO whole 4 Br2. Manganese 7 plus 4 to the 8 plus Br gives minus 1 electron each. So it will be 7 plus 8. This is 16 electron complex. And last option is Mn2CO9 Br. That means manganese is having this should be how much? 7 to 2, 14 plus 9 to the 18 plus 1. This 14 plus 18 plus 1 or this is equal to 3, 1, 2, 3. 33. This is not 36 electron, right? If both the manganese are having 18 electrons, then it should be a 36 electron complex, but that is not the case. So among the given options, only option number A is the product in which there is like which has 18 electrons. So that's why option number A will be the correct option. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So any questions from today's class? Also, now I am uploading the classes. Okay, they left already. I am uploading the classes in my YouTube channel. It will be anyways available after few days in Gate NPTEL portal. But I am also uploading the videos here, so you can go on and check. This is the name of my YouTube channel, Returani Mandal, and in description you will find Gate 20, like Gate NPTEL Inorganic Chemistry Solutions. So you will find it. And as I always say, that if you have any problem, you can mail me in this mail ID. Okay. So thank you. That's all for today. Any other questions? Okay then. Bye.